Hi guys, so this will be our first official video for MCR. In an effort to make the video as short as possible, there will be times where I pause the video to write vocab and stuff. I recommend that you pause it as well to be able to write the same. So we're on section 7.1, radicals and radical functions. First things first, I know we've talked about before, but we're going to start with the square root, which is the opposite of squaring. So for example, if we have 5 squared and we square root it, they cancel each other out because that's the same thing as 25 or the square root of 25 or 5. So essentially what the squared and square root sign are doing is canceling each other out. So not only will we be talking about square roots, we'll be talking about radical expressions in general. That means that we can have any opposite form of a exponent. So for example, the opposite of cubing something or taking it to the third power would be a cube root. So how we know what the root is this number here, or the index, where the n is in purple, and that would tell us if it's this cube root, fourth root, fifth root. If there is no index, we assume that is a square root. The radicand in green is the term that's inside. So for example, above in the square root, 5 was the radicand, and the radical sign is in black. So just one note before we go ahead and do some example problems are that we cannot have a negative in a square root. So for example, the square root of 25, the square root of negative 25 does not exist because we don't have two exact same numbers that multiply to negative 25. So for example, 5 times 5 is 25, not negative 25, and negative 5 times negative 5 is equal to 25 also. The only way that we'd be able to get negative 25 is, one of the ways actually, is negative 5 times 5, which is negative 25, but they aren't the same number. So remember, when we are not able to answer something like that, we'll call it not a real number. Remember that R with 2 lines in front of the R refers to real. So anytime you have a negative under a square root, we call that not a real number. Some other important vocab that we need to remember are perfect squares and perfect cubes. So we kind of talked about perfect squares when factoring the difference of squares. So like 1 squared is 1, 2 squared is 4, and on the other hand, we have the exact same thing for perfect cubes, as 1 cubed is 1, 2 cubed is 3, and so on for larger numbers. So if you're able to recognize those, you are able to work backwards, as well as rooting something is the opposite of squaring something. So let's go ahead and move into some examples. So although we don't see it there above in the perfect squares, the perfect square of 25 is 5, because 5 times 5 is equal to 25. So we can do that here. And that gives us our answer of 5. If you don't recognize the perfect square, you are more than welcome to put it into the calculator. Another example we might have is the cube root of 8. Now, the cube root of 8 is asking us what number multiplied by itself 3 times gives us that number, which if you look above, we have 2 cubed is 8, so we know that 2 times 2 times 2 is the same thing as 8. So that is actually our answer here. Again, in the calculator, you are able to do this. So if we were to go into our calculator and plus 8, and if you look up here in the green, there's an x square root y. So you can press second for the green stuff, the button, and then because we're cube rooting, we press 3 equals, and we get 2. So you can do that for any index. If you want to put to the 4th root or 5th root, you would just press 5. So for example, let's go ahead and write 2, And then for squaring something, we press the y to the x button, which is the opposite. And let's say we want 4. So 2 times 2 times 2 times 2 is 16. We can take the fourth root, press second, that y to the x button, 4, and it'll give us 2 again. So the calculator is kind of your best friend for these types of problems. Let's go ahead and do another one. So in this case, we're taking the square root of a variable, and in this case, we have a large exponent. So another way to write the square root sign is as a fraction, and because we're trying to find two numbers that multiply into each other, that is very similar as writing as a fraction of 1/2. So the square root sign is the same thing as writing it as an exponent of 1/2. So if you remember our rules of exponents, or our power rule, we're going to go ahead and multiply them together. So 16 times 1/2, which is the same thing as 16 over 2, or we can just cut it in half and get 8x to the 8th. And that would be our answer there. All right. So this is very similar if we were to have a cube root, where we would want to do the cube root of x to the 9th power. We can rewrite this as x to the 9 to the 1/3 power. We just write it as a fraction because we want to break it up into 3 instead of 2 this time. And now we can multiply those two together by the power rule for exponents, or find 1/3 of 9, which gives us x to the 3rd. So whenever you see an exponent in a variable, generally we would want to do it this way. And one last way that we're going to see it is as a fraction. So we are going to go ahead and notice that the whole thing is being square rooted. Maybe I didn't draw it perfect for mine, but both the 9 and 16 is being square rooted. So we're actually going to do a thing that separates it into two different square roots. You could think about this as a distributive property, because we're distributing the square root sign to both the 9 and the 16. And the perfect square of 3 is actually 9, so the square root of 9 becomes 3. And the two numbers that multiply into 16 by itself is 4. So our answer is actually 3/4. So this is the first part of the notes for section 7.1. They go along with the first assignment on Pearson